clarity wouldn't know where to look, to give them the resources to actually find opportunities to do this. So obviously it's about getting more people to participate in public science. So just quickly, there's the asteroid and the star off at infinity, and effectively the asteroid casts a shadow on the Earth. And so if you have a bunch of observers A, B, C, D, E on the Earth's surface, just in the same way that if you saw a solar eclipse, you would experience a shadow. So what you actually see is the star disappear, and then typically a few minutes later it reappears. The tracks of all the known asteroids, the data is available. Almost every possible occultation that is known about, the data is available. So in theory, one could get that data into an app and allow people to find out what's happening near them. And what we've looked at, we've found that there's actually, typically there's several occultations every night, not always in the same place, but it's far more frequent than, say, solar eclipses, which happen only once or twice a year. So there's plenty of opportunities. The asteroids are obviously smaller than the Moon, so you have to be a little bit luckier on the tracks, but in theory there's quite a lot of places where you should be able to see them on any given day. So this is what the results look. This technique's been used for years. Long prior to the internet, people have been doing this. In the old days, they used to either time it manually or use video recorders, that kind of thing. So each of these lines is an individual measuring when the shadow came and went. And if they're plotted together correctly, you get an actual outline of an asteroid. So again, I'll let Adam take over to that.
Right, so what we've got so far is a website that does two things. Firstly, it lets you view what other people have submitted. So you can see there's a similar diagram to the one that was on the slide before. So each line will represent one person's observations recorded to the outside. And this example has fewer. So on this one now, so there's two observations, one at the top and one at the bottom. And so if, for example, I was an amateur observer, I could come along, select that asteroid, save time. I can enter the start and end times of my observations. These will be the latitude and longitude of the observer, so you know where they were. And once you submit it, it adds that line straight away to the graph. So if you get, say, 20 people together on one night, they can make the observations, go home, enter the data on here, and right away you can see the shape of the asteroid being built up. That's what we've got on the website at the moment. Okay.
So we tried to go through the maths of it, which is quite complicated. So we made a lot of assumptions, which you can kind of make. I mean, like in the future we'd obviously aim to patch it all up and make it more accurate, but none of us are really capable of doing the maths for that. So we assumed all of these things. So we're just considering asteroids in the standard asteroid belt, giving them all a similar orbit. One of the main ones is that we're assuming the path it takes is looks like a straight line, which you wouldn't obviously be curved. So the calculations we've got are distorted because of that. We've also disregarded quite a few things, just considered the relative speed of the asteroid relative to the Earth by considering both their orbital speeds. So yeah, and we just assume that the asteroids are going east to west across the sky. So the shadow also follows the path. So yeah, we've also ignored the rotation of the asteroid, which you can do typically because the rotational period of asteroids tends to be sort of 5 hours or something. So in small time intervals, it's only going to rotate 1% of its axis anyway, so you can ignore it for the sake of getting a profile of the shadow that we're going to get. Yeah, so that simplified things a bit. And then, so this was using the botched maths. That is an actual past event that occurred, I think, earlier this year in January. And that's the result I got, so that's a sketch. And then this is me doing it with my bad maths. And you can see some resemblance. So given if you made it all accurate, took the curvature into account and all sorts, you could probably work out better. But this is just to demonstrate that the process works. And we could build this onto the back of our web application so that it would do an accurate picture when users enter their data and stuff. These are the problems with digital.
Yeah, just good. I should say fragmentary.
Interesting spelling mistake. Typing was one of the problems with
Typing,
yeah. Interesting.
So when we first looked at this, it was a bit of like, this sounds like a good idea, a bit like running a startup actually. When you actually dig deep, you find just how hard the thing you're trying to do really is. Maybe it was too ambitious, but one of the big things we found is that the data to enable this, even the data about what's going to happen, very fragmentary, different organisations, it's not very well organised, it's certainly not well presented. I think that's one of the things I observed is that it's very hard for anyone, it doesn't make it very accessible if you're straight into sciencey web pages that don't have the sort of look and feel of something that most people are used to. The other thing from a more technical point of view, actually being able to harness data, for example, you might have tried Google's SkyMap app, which is lovely, it's an augmented reality thing. It's also got a web-based one, but the search has been broken on that for the last 12 months. So we would hope to demonstrate getting a location and embedding it into a map, and we can't do that. So things like that frustrated it. So generally, it's hard to get at the data and it's hard to harness it. The sorts of people who store this data don't really make an awful lot of effort to make others able to use it. We mentioned the maths. Orbital mechanics is horrific. I'm rubbish at maths. Pierce and the team are probably better than me, but it's quite unpleasant stuff, and we made a lot of, I guess, quite crass assumptions, but enough to sort of prove the point out. Obviously, our lack of astronomical expertise, the potato is quite helpful in sort of visualising which way would the shadow track go.
I think I had east and west mixed up for a long time.
Yeah. This is, I've got this data. This is some previous observations. These are individuals who've made observations, start times, end times, and their grid references. This is the kind of ugly data that one can get. It's not made easy. And obviously, if we can do something that not only helps collect data, but then aggregate it and process it, then potentially make this a much easier thing to do. What next? If we were to take this further, we would try and integrate the things that are out there. We discovered, thanks Ed, a thing with JPL we call Horizons, which is an ephemera, so basically it's allowing you to find out all sorts of data about orbits of things. If that has an API, or if we can get at it in some way, then maybe we can integrate more things into the app. Clearly making the maths real, our approximation I think proved a point, but there's an awful lot of things you need to worry about there, so it requires a mathematician and an astronomer, I would say. Ultimately, we'd like to create a native app for people's mobile phones as well as a web version, and also to make a public website to encourage people to do it, to share the results, and to actually see the final plots that have come out of it. So I think that is it. Thank you.